from 1 up to 2 of x times the square root of x minus 1 dx. Okay, so here is our antiderivative that we want to evaluate. It's a definite integral. So a few things. Number one, I'm going to need to make some choices about my u. I'm going to need to change some boundaries. Okay, so when I look at this, Dennis, did you try any possible u's for this one?
Well, I ended up figuring it out, but I had to call my buddy, but I put u as x minus 1.
Okay, so that's a really good first choice. So thinking, okay, I see a square root, and I see something under it. So choosing that value underneath the square root is a really good first idea for a u substitution. So we might try it out, and we'll let u be equal to x minus 1.
du equals dx.
Yeah, so this is a really easy derivative. Here our derivative du over dx is equal to 1, and so dx is equal to du. So life is good in that category. Along with that, some other work I'm going to do over here on the side. I'm going to change my boundaries. So when x is equal to 1, then u is going to be equal to 1 minus 1, which is 0. So my bottom boundary for my u values will be a 0. And my top boundary, when x is equal to 2, then u will be equal to 2 minus 1, which is 1. So our top boundary, or u boundary, will be 1. Okay, so now we go ahead and we plug in some values here. We've got an x, and then we have the square root of u, which is the same as u to the 1/2, so I'll go ahead and write it with that power of 1/2. And dx is exactly the same as du. And so here I get to this point. I've made my substitutions for u, I've made my substitution for dx, I've changed my boundaries to u boundaries, and now I'm sad because there's still this x dangling in here, and I'm not really sure what I'm going to do with that because nothing canceled it. Okay, so where does that go?
It's just forcing the u down its throat in a way where
Yep. So we're being a little violent here. So one thing that we can do is that we can go a step beyond the standard u substitution and say, okay, I know that u is equal to x minus 1, which means that if I solve this equation for x, I get that x is equal to u plus 1. And so it's totally legitimate that any place that I see an x, I can replace that with a u plus 1. And so here I now have the integral from 0 to 1 of u plus 1 times u to the 1/2 du. Now that may seem like cheating, but I'd like to encourage you to think of it rather than cheating as cleverness. And so we've made this extra substitution that's gotten rid of that extra x. So once you've made a choice about u being equal to something in terms of x, you are welcome to manipulate that equation and use that to make other substitutions later on if you have what I would call dangling x's, leftover x's. Okay, any questions about getting to this point? We're happy because we're all in terms of u's. Okay, so at this point, we're not quite ready to take an antiderivative because we have multiplying going on. So before I can take an antiderivative, I need to clean up these parentheses, which means distributing this u to the 1/2. So I'll end up with the integral from 0 to 1 of u to the 3/2 plus u to the 1/2. So that's the algebra part. Still no calculus has actually happened just yet. And now I'm ready to take an antiderivative. But I think from here, you might be okay going on from there. But that's the hard part, is getting all in terms of u. Next step is to take the antiderivative. And then the next step after that is to plug in the boundaries. Plug in the u bounds and subtract. Okay. Okay, any questions about this one? Yes, Mike.
So what type of visual cue do you see when you start doing that, when x is equal to 1 and u equals 0, and x is equal to 2 and u equals 2
What-
minus 1?
What do you mean by that?
Like how do you know to start doing that? Like,
How do I know to do this part right here?
Yeah,
So if I have a definite integral,
yeah,
and I choose to do a u substitution, then I want to make that choice to change those boundaries. If it's an indefinite integral, if I have no boundaries on that, I don't need to worry about that.
okay,
And the only time that I need to change these boundaries is when I initially look at this problem, I say, okay, these are our x values. I know that they are x values because of the dx at the end. And so once I'm changing things into u's, I need to make sure that every part of the problem is related to a u rather than an x. And if I had kept these original x boundaries, it wouldn't match my new variable.
so this is an indefinite integral, you said?
This is a definite integral.
So every time you do a definite integral, you have to do that step?
Yes. The other option is pretend like it's an indefinite integral, find the antiderivative, and then plug in the original bounds. But if you want to keep it as, as a policy, then u substitution on a definite integral, change the boundaries.